Thank you. I am grateful for the opportunity to present this work on behalf of my colleagues. Shunpin Wu is with Zoex Corporation in Houston. Qingping Tao is with GCmSQP2010 LLC. And I'm also affiliated with GCmSQP2010 LLC. And then two biologists at the University of Nebraska, Sally McKenzie and Jingxing Xu. I'll be talking today about metabolomic analyses using comprehensive two-dimensional gas chromatography with mass spectrometry. So this is the outline of my talk. I'll first set out the goals of our work. I'll talk about samples and sample preparation. I'm a computer scientist, so this is not something I know anything about. But I'll tell you what was done. And then I'll talk about comprehensive two-dimensional chromatography with mass spectrometry. And again, since I'm not a chromatographer, I'm not an expert, but I've acquired a bit of knowledge over time, and I can tell you about those technologies. Then the work that this talk focuses on, which is the data visualization, processing, and analysis, and some preliminary results. And then I'll finally talk about conclusions and future work. So the goals of this talk of our work were to discover and document compounds with different relative concentrations among sample classes as potential metabolomic biomarkers, and of course that's been sort of the subject of discussion this morning. Then secondary to that primary goal is to develop and demonstrate effective analytical methods for metabolomic analysis and data analysis. And so we both wanted to work on the analytical chemistry and the data processing problems with this goal. So next, samples and sample preparation. The samples were Arabidopsis, which is a kind of small, I guess it's something like a mustard plant. I don't really know very much about it, but it's got a small genome, and it was one of the first fully sequenced genomes, and so it's a popular model system, and which was all of those reasons why we selected it for our work. This particular data that I'm going to talk about today includes only two sample classes: control wild type Columbia 0 and an experimental mutant class. And we have some later work with some more classes, but the things that I want to talk about today are it's sufficient to talk about these two classes. And we have 3 experimental replicates, plant samples of each class, and that's why, of course, this is merely a prospective method development, not final results. You'd certainly want to have more replicates than that in a real study. So the sample extraction, my cartoon understanding is they crush up the leaves, they do some chemistry to them, and then they're ready for chemical analysis. But there was, to help with the chemical identification, the insertion of a marker to help with the, although that turned out not to be a very difficult problem to get the retention indices. So the technique that I'm going to talk about today is comprehensive two-dimensional chromatography with mass spectrometry. And some of you I know are familiar with this, but some may not, and so I am going to talk briefly about this technology. So the technology uses a modulator to trap the eluent with analytes at the end of the first column. And in this case, we're using a thermal modulator with gas chromatography, so it essentially imposes a cold spot to trap the output of the first column. And this is, the trapping is done for a relatively short period of time, in this case 10 seconds. What you're trapping is 10 seconds of the eluent, and then it's heated suddenly to release it into a second column that separates on a different chemical property. And so this is repeated every 10 seconds, trapping the release. And the separation in the second column is done, it's a very short column, it's done very fast. And so this gives us a separation time in both the first column and the second column. The two column types are here. The runtime was about 2 hours. There's an oven ramp to accelerate the analytes, and we're using EI, electron impact ionization, and the acquisition rate is fairly slow by GCxGC standards, 50 hertz. Now in this case we were using the Shimadzu GCMS, which is not a high-res instrument, but we have since acquired data on a high-res mass spec instrument, which will allow us to do some work with elemental compositions as well. And there were 3 replicates per sample, so a total of 18 runs for the 2 classes, 3 experimental replicates and 3 chromatographic replicates. So this is the main part of the talk that I want to present. So here, this is what the chromatogram looks like. Along this axis of this is the first dimension retention time. So this is the time of the analyte through the first column, and you can see here what a traditional 1D chromatogram would look like projected on the backplane. It's a little washed out, the light in here, but you can perhaps see that one-dimensional chromatogram there. Then each of the trapped analytes at the same time are separated on a second column, and so this is 0 to 10 seconds through this axis, and you can see the distribution of peaks. And you can see that one of the things that two-dimensional chromatography gives you is a separation of analytes that otherwise in one-dimensional separation would be co-eluted, and so you get much truer spectra for each of your analytes. And you can see this is a very complex sample. There are certainly hundreds, and I'll get to numbers later, but there are certainly many peaks that can be seen here. The third dimension is, in this case, the total ion, total intensity chromatogram, the digital number produced by adding all of the ion counts at each level of the mass spectrum. So the primary focus of this work is how do you extract the data from each of these chromatograms? How do you align all of the data across samples so that you can compare, in this case, just a few chromatograms, but in the larger studies we've done, up to hundreds of chromatograms. So this is the sequence of work in the GC Image Investigator. Each chromatogram is processed, and the processing, the first step in the processing is to remove the baseline of the detector. And one of the nice things about two-dimensional chromatography is you have large regions of the retention time space in which no analytes, and so you have a good picture of the detector background, and it's fairly easy to remove. Then we do peak detection, which in 2D we call these blobs, and because they're not just single dimension peaks, but peaks in 2D. So having determined where the peaks are in all of the individual chromatograms, what we want to do is to find the reliable peaks by pairwise matching. So we take each chromatogram, we take the pattern of detected peaks, and we do a sophisticated pattern matching algorithm to match it to the patterns of peaks in each of the other chromatograms. And through this you get a sort of matching graph that connects each chromatogram to every other chromatogram. And through that you can find graph structures that give you peaks that are reliably found across all or many of the chromatograms. And so using those so-called reliable peaks, we're able to align each of the chromatograms on the basis of those same peaks in each chromatogram. And our next step then is to create a composite chromatogram. By aligning each of the chromatograms, then we add them up, although other means of compositing would be available. In this case, we just add them up. and get what we call a composite chromatogram. The idea of this chromatogram would be that you get in this composite chromatogram every compound that was present in any of the chromatograms, and hopefully in the correct retention time position relative to all the other chromatograms. So then, having this composite chromatogram, we do a little bit of the same processing on it. We remove the baseline, then we find the peaks. And so we've detected hundreds, perhaps even thousands of peaks in this composite chromatogram. And rather than trying to find those peaks in each of the chromatograms, what we do is we use each of those peaks in the composite chromatogram to create what we call a peak region feature, which is just a two-dimensional chromatographic window. And we also incorporate all of the reliable peaks. And so we have this pattern of reliable peaks and then retention time windows around all of the peaks that we found in the composite chromatogram. And I'll show you a picture here next. So here's the composite chromatogram. You can see it's a sort of laid out flat version of the three-dimensional chromatogram that I showed earlier, where colorization is used to show where the peak intensities are larger. And in this case, we found 72 reliable peaks across all of the chromatograms, and those were then used to align the chromatograms to form this composite chromatogram. Then we detected all the peaks in this composite chromatogram, and we drew well, we didn't, the computer did, drew a region around each of the peaks that was detected. So the idea of having this, what we call a template, the idea of having this template is that this can then be used as the basis for analysis of every chromatogram. We have reliable peak positions, we have peak regions that are defined relative to those reliable peaks, and we can take this template and match it back to each of our chromatograms and determine what's the response in each chromatogram in each of these regions and do a comparative analysis. So that process is summarized here. We match the feature template to each chromatogram by matching the reliable peaks to the detected blobs in each of the chromatograms, and then we geometrically adjust these peak region features relative to the matched peaks so that the same relative position is maintained by all of these 2,000 some windows that we are going to characterize for each chromatogram. Then we record a feature vector with the detector response for each peak region feature in each chromatogram. And I'll show a table of that in just a moment. And in this case, we're just using what we call the feature volume. It's the 2D analog of a 1D peak area, focusing on the tick, although you certainly can look for features according to the specific masses within each peak. We're also particularly interested in the percent response. In this case, we don't have an internal standard, so we're normalizing the response in each region against the total response in every region of the chromatogram. So it's a relative percentage of each peak region in the chromatogram. So in the end, you get a table where across the top you have all of your individual chromatograms, and down the rows you have each of the regions that you saw outlined in the composite chromatogram. And so then in the table itself you get what's the response in each region for each chromatogram. And in this case we're looking at the percent response of each peak in each region. And of course then with this kind of table you can begin to do analytical studies of which compounds are different in the different classes of compounds, in this case between the wild type and the mutant Arabidopsis. So some of the statistics you can use are the means and the standard deviations, relative standard deviations. We look at per class means and standard deviations, and then you can look at the class-to-class differences, and in particular we look at the multi-class Fisher Linear Discriminant ratio, and if there's multiple classes, you can look to class or class to other ratios. And peak regions with large Fisher ratios are those that have different means in the different classes, and that the mean difference is large relative to the standard deviations that are seen within each of those classes. So these are just some preliminary results from this work. This is kind of washed out, and so it's a little hard to see that there are actually some spots over here. But the way that this works is that this is the Fisher ratio. So the better separation that a peak has in terms of difference between classes, it's further out on this scale. But one of the things that happens is in metabolomics, it's often difficult to have enough samples to be confident of your results. So if you only have a few samples and you have thousands of features that you're going to compare for differences just by chance, you know, something that doesn't have a difference but 1 in 1,000 times it would, you're going to find some differences that are a result just of the pure chance. And so one of the things we do is as a validation, in this case, leave one out, cross-validation. In this case it was nearest neighbor accuracy. And so you can have high Fisher ratios, but it might just be apparent that there's a large difference when really, so what we're looking for is things that are up in this region, that they're valid and there are large differences. And I think maybe you can see one there. I don't know. It's, as I say, I apologize. This slide is pretty washed out. Oh, one other comment. The size of the circles is the mean percent response. Some of these might be interesting as well. This one doesn't show much difference, but it's a very large compound in the analysis. So then we're able to extract those features with very high Fisher ratios. This means that they're widely separated with respect to their means in the classes, and that they're also highly reliable. And additional features could be investigated as well. So you can see here that this is in the chromatographic space where each of these very promising features are located. And then especially with the high resolution mass spectrometry, it allows you to focus your interpretation of identification on these most promising differences. Again, this one is pretty washed out. It doesn't, I guess this one here you can sort of see that there's some separation. What you're seeing is one peak's response in this axis and another peak's response in this axis of the 8. I've made four different pairs, and you can see that this group is widely separated from this group. Again, I apologize that this is so washed out that it's kind of bright in here. You can kind of see this here as that's the problem with developing slides that look good on your screen and on your computer screen, and not. It's a little better, but still not too good. On my computer screen, this looks pretty good. So I apologize for that. You can see some green ones up here, though, with the lights down. You can see some green ones up here, and I guess I was mistaken that the green ones are actually up here and over here. So probably a couple people up here right in front can see them better, but I apologize that these are a little washed out. I need some bigger symbols, I guess. So then, for identification, we used several metabolomic databases, the NIST, Wiley, and so on. And of course, the library hits are very unreliable. for a variety of reasons, as already been talked about. When I first got in this as a computer scientist, it was explained to me you just match the spectrum against the library, and that would give you the chemical identification, but that's wildly inaccurate, that claim. So pruning the hit list by retention indices, though, proves to be quite helpful, but still there are problems with the compounds not being in the libraries, and so it's not a straightforward task there. Here's some of the retention, the compounds that were used to indicate the retention indices. That's, again, not very interesting, but it did allow us to do some pruning. And you can see that there's a little glitch here in the retention index calibration. Probably that one should be left out, but there's a very nice curve there between retention time and retention index of those marked peaks that were in the slide I just showed. We also used both, compared the apex spectrum, the single spectrum that is the largest, as well as the sum of all within the blob, and if the sum is equal to the apex, then that's an indicator that there's a pretty good peak purity. There are, of course, other measures of peak purity as well. Here are some slices, one-dimensional chromatographic slices through the two-dimensional peak for various ions. You can see that it appears that there's just one peak, and so this again is confirming that this is a pure peak. The spectral hits are not uniform across all these, and so the retention index does help sort of say, well, you know, it's not going to be this one here. This one looks much more promising, even though the hit ratio is the match factor is a little bit lower. So this is still a very difficult part of this work, even with the high resolution mass spectrometry that we have in a later data set. So one of the things that's very clear is that the two-dimensional chromatography provides much better peak resolution than traditional one-dimensional chromatography. The problem of coelution is much, much smaller. The approach that we're using for peak region feature analysis is able to characterize large numbers of chromatograms with relatively limited use of peak matching. We were able to match a few peaks to align the chromatograms and then look at chromatographic regions. And identification, however, still remains a very challenging problem. So certainly the isotopic analysis would be very, very helpful in this regard. So our future work, we've already acquired some high-res mass spec. We've increased the mass to charge limit. I'd like to see this even a little bit larger. One of the challenges with the high resolution mass spectrometry is that this work requires very high speed mass spectrometry. You can do it down to 25 or 30 spectra per second, but that's kind of at the low end. You know, we'd like to get up to 50 or 100 at least. The more recent data has 4 sample classes, and so we'll present this in May at Riva del Garta, which is the GCxGC meeting, and one of the most beautiful places in the world. So that's why I go there. It's just good that the conference is there. Thank you.
Wasn't clear what you said at the end about the isotope ratio part. Are you guys, for now, just throwing that data away because it becomes too complex to use it, or is that part of the model and fitting and figuring out what's going on?
No. Yes, we certainly do the isotopic analysis you know, based on the high resolution mass spectrometry, but there's no introduction of any isotopes. This is just the naturally occurring isotopic patterns can be used, but no, we do use that as a confirmatory for identification.